This is PreCalc section 3.1. This is day 1 of 3.1. We've got day 2 tomorrow. Today we're going to write and use exponential and logistic functions, graph and transform exponential and logistic functions, and understand and use the natural base E. I don't know about understand and use today, but tomorrow we'll be using more of it. Use exponential and logistic functions to model population growth. Now, as we're looking through these, if I can actually make this work, maybe. Yay. Okay, the definition of exponential functions, let a and b be a real number constants. An exponential function in x is a function that can be written in the form of f of x is equal to a times b to the x power, where a is my initial value, okay, and b my base and x. And you guys should be pretty familiar with this. This should be something you saw in Algebra 2. Okay, where a is a non-zero, b is positive, and b isn't 1. The constant a is the initial value, and we call it the initial value because when we put x in as 0, that evaluate b to the x power evaluates as 1, so that's your y value for your y-intercept. And the b is then the base. So knowing those things, I want you to look at these next 5 examples and consider, determine whether each is an exponential function, and for those that are exponential functions, identify the initial value and its base, okay? So you're just using what they just talked about, defining what an exponential function is, to, hey, is a an exponential function? And you're looking at a and you're going, hey, it's raised to the x, and up here in the definition, it's raised, b is raised to the x. So I've got an exponential function. I happen to have my initial value of a is 1, and my base value is 3. Okay, when I go through that. So my initial value, my base value, if I bring them up, but I can't, so my initial value should be 1, and my base value should be 3. So really I'm saying this is 1 times 3 to the x, where a is 1 and b is 3. Okay, and perhaps to do that more correctly, I've got that. Now, in b, is it an exponential function? Can I have a base be a variable? I've just got it raised to the -4 power. So I don't have a situation where I can have the base as a variable. It's got to be the exponent. So this is not. Base is a variable. Now that you've got a couple examples, you guys go after the other 3 real quick. See how you're doing. I'm just reading your shirt. Now, as we're going through this, I got my base is 1.5. My initial value is -2. Okay, here, exponential function. And D, I got my base is 2. My initial value is 7. Maybe my base is 2. Gosh, it just like it exists and it doesn't exist all at the same time. Okay, but this is a different type of exponential function. Do you see this one as a decay? Okay, from left to right, it's going to decrease. As I look over this, and it's reflection over the y-axis because that negative's inside the function. Okay. And in E, some people go, well, it's raised to the pi. It's a constant. I mean, if I put all that in, it's going to be a horizontal line going across. So that's all that is. 6 to the pi power, which is a little bit more than 3. 6 to the 3rd power times 5. It's a really high, on the y-axis horizontal line, but it's a horizontal line just the same. Questions about these? Questions about identifying? Good? Okay. Sliding down. One way to evaluate an exponential function when the inputs are rational numbers is to use the properties of exponents. Well, I'm not going to run through all the properties today, but we will. Okay, get to most of them. But I'm just asking you to put in 4 in terms of x for x, so that's 2 times 2 times 2 times 2. Just to review, you guys had this as algebra students, as 8th graders. Okay. You had it again in Algebra 2. We also had an Expo, okay, as freshmen, if you were here at the high school. And we're just going, hey, that's 16. Okay. Now, did you have to show it's 2 times 2 times 2? No, I just want to make sure people review this as we go through. I get a lot of people that do go 2 times 4 and go, boom, why is it 8? Okay, so that's why I'm doing it. After 0, anytime I raise something to 0 power, it's just 1. And go ahead and do the next 3. Go ahead and do the next 3 on your own as we're going through this. Now when I raise it to the negative power, that flips it, so it's a half times a half times a half, and so I've got an 1/8 going on here. That's what that negative does. It just does the reciprocal of the original, of the stuff inside. It just does a wholesale flip-flop. And when I raise something to a fractional power, I'm asking in this one, f to the 1/2 power, if I got it to the fractional power, I'm actually looking for the square root. 1/3 power, I'm looking for cubic root, and so on. So that's what I'm looking for. Thank you, dear. So I popped that in, I got the square root of 2. If you put it in your calculator, I got some people who will go through, and again, this is to 3 digits, 1.414. And then E, when I'm looking at that one, geez, that's -3/2 power. That's like messed up. But remember, I'm going to flip the stuff that's inside. So it's going to be 1/2 raised to the 3rd power, but the square root of that when I look at that. So I've got that, and I can write it like that, and 1 over the square root of 8. And right now I've got some people going, oh, Bloom, you got to rationalize that. We can have the square root on the bottom. Right? So technically I should be looking at a problem that does this, and then multiply and see the square root of 2 all over 4 as I get that going. Questions regarding these at all? Rationalizing things, doing one thing over another. There we go. Now, there are going to be times I have to use a calculator because we're using irrational powers. So if I have a f of pi, so I've got this to the pi value, it's possible, you got it, you've got the capacity to do it. It's 8.825 in terms of 3 decimals. I can raise it to the square root power if I need to. So we can do that, and it's 3.322 as we kind of cycle through these. Now, as a reminder to review us about these, finding an exponential function from its table of values. You know, they've got this stuff going on here, and I want to talk about this a little bit differently at times, but remember when I'm talking about an exponential value, we're always talking about the initial value, okay? Then the initial value is when x is 0. The initial value normally is where it crosses the y-axis. So when x is 0 and I got 4 and I got 8, my initial values should come out here And I should know right now my a values are 4 for the g of x function. My a value is 8 for the h of x function. Does that make sense? Why? Because at the point where I have x equals 0, I get 4. So I'm saying that I'm raising my b value to the 0 power. And I'm multiplying by my initial value, my a value. So right now, I know that my g of x function looks something like this. So I got to find out what that is. And my h of x function looks something like this, and I've got to find out what that is for that function. Now, if I look at this and I notice that it's just multiplying by 2 as I increase, as I go up from -2 to -1 to 0 to 1 to 2, and I just notice that I'm multiplying by 3, so I'm just going up by 3s as I go. And here I'm going, as I go along, I'm actually decreasing or making my function smaller by a fourth. I'm dividing by 4 or multiplying by a fourth. So that allows me to find my b values as I look at that. So I have my a's and my b's that I can use to actually write the function from a list of coordinates. Are there any clarifications for how I found the initial value, why I was able to call it the initial value, my a value? So when 0 goes in for x, my base becomes 1, b to the 0 power becomes 1, and I'm able to say that's my initial value. And then from there, based on my results in my table, I can determine other things. Okay. That was really nice because our table went up by single values from -2 to -1 to 0 to 1 to 2. So it allowed us to find it easier. Sometimes it's not as nice. Questions about it? Okay. Now, I was doing this earlier today and I was like, there's a method that I'm going to show you, but I want to show you the mirror method of what we're used to doing. And that for this, we're going to find the exponential function. Remember, the exponential function, our general form is right here. Okay, so that's the general form of my exponential function. Okay, that's the thing we're going to do. Okay, so I got f of x is equal to a times b to the x power. Well, when I'm given the values that I'm provided, -2 and 10, and 2 and 1/3, remember, the first one's always x and the last one's y. Well, that's my f of x value. So I have two equations as I'm looking at this. My first one is 10 is equal to a times b to the -2 power. That comes from, perhaps I should just go with this. That's my equation 1. Okay. And my equation 2 is coming here from that set of coordinates. I want to make sure you see what I'm doing and how I'm getting those things down. Now, as we're looking at this, I thought it was kind of a cool thing. I'm going to show you one way that I thought it was cool. I have not seen it this way, but I'm also going to show you what you've seen before. Okay, so you can say, hey, I understand what I'm doing here. I'm setting up a system of equations. Remember, we've done this a couple times where we have a couple different equations and we can set up a system by plugging one value in for another to find other parts of the equation. So if I'm finding b, if I take the two equations and I divide, okay, if I divide one equation by another one, okay, so I take my 10. And why did I use 10 on top and the fraction on the bottom? Because when I do this, it gets rid of my fraction in a way, okay? It just made it easier. It doesn't matter which one I decide to do with this, but when I do this, my a's cancel, okay? So I get it down to one variable, b, okay? I find out what my b variable is equal to. And some people are like, okay, all right, I can do that. So now I've got b to the negative 2 divided by 2, which is b to the negative 4, and this is 30 on this side. 10 divided by 1/3 is 30. So I got 30 b to the negative 4th power. Now I can find b, right? No problem. I can just go ahead and take the multiply negative 1/4 on both sides and find out that 30 to the negative 1/4 power is equal to b, because this will multiply to be just b there. Now, when I saw this method, I thought, hey, that's pretty cool. That's a really quick, down and dirty way to get my one single solitary variable. But when I do stuff like this, as a student, you're like, this is completely different and new. No, it's the same stuff that we've been doing. Keep in mind, I know that these two equations are related, okay? So if I take one of them and solve for the other, like one of my variables and plug it in, I can find one of the variables I need. And I'm looking for b. So if I decide to take 10 is equal to a times b over negative 2. Sorry, folks. This is kind of doing some stuff to me. Okay, so if I do this, and I already know that I've got a is equal to 10 over b to the negative 2. That is equal to a. Are you in agreement that a is equal to that? Well, where I see that in my other equation, my 1/3 equals my a value of 10 b to the negative 2, okay, times b squared. I find out that b to the negative 4th, and if I multiply it by a 10th, so it's 1/30th there, that works. And I end up finding out that 30, if I flip them and multiply by negative 4th, 30 to negative 1/4 is equal to b. Finally, can do that, because all I'm doing is systems of equations. Okay, I always get students wondering, why did you do it? This is just faster. Okay, dividing the two. Okay, but I could find one over the other, no problem. Now, after I do that, I've got my b. I got to find a. Okay, so when I'm looking at my a value here, I'm checking out that I've got an a value here, but I'm going to pick one of my values in my previous equations, and I'm going to use the 10 because that was an easier one to do. So I'm going to put 10 is equal to a times the quantity 30 to the negative 1/4 power goes in for b. And now I'm going to evaluate for my a value, because I already know what everything else is. I just got to find a. So I'm going to multiply by negative 2 and negative 1/4 this power here. That's where that 1/2 comes from. By the way, that's the square root of 30. Okay. So now I'm going to divide by the square root of 30, or the square root of 30 halves. Okay. And now I have my a value. But I could also look at it as 10 times 30 to the negative 1/2 power. So I can look at it like that as well. I don't care which way you use your a. Now I've got my b and I got my a for my equations. And what I was supposed to do is be able to come up with my function based on them providing me two different points. Are there any questions about the stuff I'm doing? Nothing beyond what you're used to doing. Okay, it's just make sure you're showing everything together. And now I've got my a and my b. I got my original function, and I put my a value in, I put my b value in, and now I evaluate my b value powers. So I've got negative 1/2 plus negative x over 4, okay, which is negative 1/2 minus x over 4. Now I want to kind of step out for a second. If you're in a multiple choice test and you're asked to find the function, okay, and you're evaluating this as you're going, they could have their answer in a different way. What happens if I factor out a 1/4, a negative 1/4 out of that power? I could have it come out as negative 1/4 and it be negative 1/4 times the quantity 2 plus x inside, or x plus 2 inside that power. Just depends on how my answers are written, because any one of those three is the same answer. Okay, so in a multiple choice test, if you're asked to find a specific value, manipulation of your exponent may not be unheard of. Okay, and some people say, well, I'll just plug in the numbers. You could, and you might get something that'll work, but be careful as you're going through those. But remember, all I did was systems of equations. I had two equations. I solved one for a variable. I plugged it back in to solve for the other variable. And then I put them both in to show what the function was. Okay? Now, values of a general exponential form. Pattern leads to the following recursive formula. Okay? So we're looking at this, and we're talking about the general exponential function, and we are multiplying by b as we go. So we got this recursive formula, which is interesting to me, that they talked about it this way. Keep in mind f of x here is this value, okay? So if that's f of x, we're looking at the idea that f of x, and they're just taking b times f of x, which is a b to the x power. Remember, that's b to the first power. If I was going to combine like terms, wouldn't this just become a b to x plus 1 power? And so they're kind of driving it, hey, this is the same as putting x plus 1 in for x. And that's what it is. Okay. Now, if a is greater than 0 and b is greater than 1, the function of f is increased and is an exponential growth function. Okay. So it'll go from left to right going up. The base of b is its growth factor. Now, if a is greater than 0, but your b value is less than 1, okay, and really between 0 and 1, it's not negative at this time, we're talking about between 0 and 1, is decreasing in an exponential decay function, okay? The base b is its decay factor. Are there questions about it? You've seen exponential growth, you've seen exponential decay. We're defining it again, and we're looking at this. And what I'd like you to do is go ahead and put these in your graphing calculator, and apparently somebody has left something there, so that was supposed to be hidden. We're just going to take care of it as we go. Nothing is working today. Okay. Pop these in your calculator. Notice what's going on. Look at the value that all of them will have. I think I give you a hint on what that value will be. Make sure that you can pull those up and you're comfortable with the use of your calculator. It's easier if you see them. Did you get an invalid dim? Go to y equal. Here, let's hit quit and let's go to y equal. You see that plot? Turn it off, which means you just got to go up there, hit enter, and then go back down. Now it should work. You're getting something like that, right? We doing okay? All right. Part of this is for me to just kind of go over calculator use too. Yeah. we've all gathered here today to commit the calculator to the earth. Okay, yeah, it needs a little bit of a charge. Okay, I've got one on my desk if you want to borrow one. Or we can just nickname your calculator Blinky. Okay. Which points in common? 0, 1, that's right here. All your graphs will go through in general form there. 3, 4, 5, 6, 12. And that makes sense because, you know, the initial value is found when x is 0 and anything to the 0 power is just, except for 0, is 1. Okay, so now we're asked to analyze the functions in the domain. Okay, so let's talk these out. Domain, from negative infinity to infinity, totally works, totally continuous. Okay, range, from 0 to infinity, not including 0. Increasing, decreasing behavior. Okay, it's increasing, and we're talking from left to right. Okay, as the function goes left to right, what is happening with the graph itself? It keeps going up, right? So it's always increasing from left to right. Symmetry, it's neither even nor odd. Okay, it's boundedness, it's bounded below. It doesn't go below the horizontal asymptote of y equals 0. The extrema, there isn't any when you look at the graphs, each one of them separately. Asymptotes, we don't have a vertical asymptote, but we have a horizontal asymptote of y equals 0. And end behavior. Well, and I'm looking at end behavior from going towards infinity to the left, my graph tends to 0. My horizontal asymptote, hey, that kind of makes sense because horizontal asymptote is all about end behavior. As I go to the right, going to infinity, my graphs tend to infinity here. So the information that we've just talked about is all right there. And the reason why I just talked those out, pointing at the graph, is because the next one is working with decay values, and based on the information that we talked about, or at least I described and explained in problem 1, I would like you to fill in the information in problem 2. Get that up a little higher for y'all. It worked really good earlier, and it's not working at all now. Okay, so do you guys get this graph on your next one? Everything's still going through 0, 1. Okay, totally makes sense still. Initial value is when x is 0. That's called the y-intercept, the initial value. Okay, and that's true with most of our functions that we work with, unless they don't cross the y-axis, and then we got an issue of not having that initial value. When I'm looking at the domain, it's continuous from negative infinity to infinity. When I'm looking at my range, it goes from 0, I should say it goes from 0 to infinity, but you know, it's bounded below, okay? So I'm looking at this. It's continuous. It's decreasing from left to right. Not symmetric. It's bounded below. Symmetry, boundedness. We've got no extrema because there isn't a local max, local min. It's continuous. Horizontal asymptote again at y equals 0. My limits. As I go to negative infinity, it tends to infinity. As I go to infinity, it tends to 0. And that's where that horizontal asymptote stems from. This should be 0, and this should be infinity. My end behaviors. Let me get those higher. It's going to drag my feet a little bit longer. People are almost done. Now, the information that we just did in the last two questions is kind of summarized on the top of the next page. Okay, you're looking at exponential growth and exponential decay. And they talk about that they're continuous, there's no symmetry, bounded below both of them. There's no local extrema, horizontal asymptote y equals 0, no vertical asymptotes on either one. Okay, b's greater than 1, then f is increasing function, and those are limits. If it's between 0 and 1, that's important. Okay, between 0 and 1. Because remember, if we have it become a negative value that reflects, okay, so we got to be careful. It reflects over the x-axis. If we have a negative b, not a negative exponent, but if our b is negative, it does a reflection, okay, over that x-axis. Questions about these so far? Okay, translations, reflections, stretches, and compressions. Now, these are all compared to our parent function of being 2 to the x power, okay? What I want you to be aware of is that stuff inside, like x minus 1, that moves it 1 unit to the right, okay, in the exponent. Stuff inside acts differently and behaves differently, and it behaves, you know, it's like a reflection in b, we got a reflection on the y-axis. So let's talk about this one thing at a time. So when I'm looking at this next graph, I've got that, and I should have had my graph up here, and it is. I'm not sure why it's not there, but this is the joy of setting things up and then having it blow up on us. We'll do this up there. You guys go ahead and write that down, and I'll get that up. There we go. So you notice that it translated to the right 1 unit as we look at the original graph that was blue. So it'll be a horizontal translation, right 1 unit. Here, if I'm reading here, that negative with the x, it's not a negative on the 2. It's not a negative in front of the 2, I should say. Okay. And perhaps this is a really good opportunity for me to go over functionality of your calculator as well. Would you guys all be so kind to put in 2 raised to the 4th power and negative 2 raised to the 4th power? Because a lot of times students think differently about these. I want to make sure you realize order of operations on your calculator. I actually had a student teacher sitting in back say, oh no, they're both the same. They aren't. Remember, order of operations requires me to do exponents first. So 2 to the 4th power is 16, and then take its opposite. So this one is actually equal to negative 16. This one is actually equal to 16. Okay, and a lot of times we do things so quick in our heads that we think, oh, it's even, it's fine. And it would be if I did that, then it's 16. So be careful when you see those powers and what you're doing with your calculator. And I'm only pointing it out because it's something that we will come across in this section. Okay, now, in this one, I've got a reflection across the y-axis. Okay, so it's going to reflect across the y-axis, and as we learned with reflections, okay, if our nose is on the reflection, say a mirror, and we put our nose on the mirror, our reflection's nose is on the mirror. The idea of this reflection, it reflects across the y-axis, so it's the same distance away here. So we reflect over the y-axis when we have that negative inside the function. Okay. In our last one, we have a vertical stretch by a factor of 3. If we can get that over and going, and we'll pop that up and see what a vertical stretch by a factor of 3 might look like from the original function to the changed function. Now, are you to recall with the stuff inside the function behaving opposite of what you'd think would happen? Instead of moving, we subtract 1, but that's really moving the function one place to the right. We multiply by a horizontal by 2, but that's really doing a vertical shrink of 1/2 from our work that we did with parent functions in section 1.3.1.4. Now, what if the base of 2 in the last problem was replaced by 2.718? Now I'm saying, hey, if I had you take y1 and be 2 to the x, and then y2 was 2.71828 to the x, would it be similar? Please graph those. And try to knock off the other graphs that you have on your calculator as well, so you can see those two come across. It's so exciting watching them in their color. Now it's a little different, isn't it? Do you see it? Just a little different. It comes across, but it goes up faster, that 2.718. Okay. Graph doesn't change much, it just goes up a little higher. Okay. But we're going to talk about that change a little bit. You've seen this before, this number. It's E. We're going to talk about what's happening between the two. One goes up a little steeper. Everything meets at 0.1, but the 2.718 increases faster because it was bigger, okay, as I'm taking the square. Now we got that natural base V. Okay, you guys talked about natural logs. It's base E, 2.71828, as we're working with that versus base 10, where it's the log of base 10 when we're working through with them. So now we're looking at exponential function, It's just kind of a review of what we just looked at. It's one of the basic functions introduced in section 1.3 and is an exponential growth function. Okay, remember, it's bounded below, horizontal asymptote, y equals 0, from negative infinity to infinity. That's the domain. The range is 0 to infinity. Okay, there isn't any sort of local extrema or anything for maxes or mins. We're looking at vertical asymptotes. There isn't one, but again, it's a horizontal. And remember, the horizontal is really defined by its end behavior. Okay, one or both going on a value, coming in on a value tells you where your horizontal asymptote will be when we're looking at end behavior, because it's where the end of the graph will tail to. Okay, as it approaches negative infinity, it's going to tail to 0. That makes sense. As it goes to infinity, it goes to infinity. Okay, as we look at that. So it wouldn't have a slant asymptote here. Okay, because we have the horizontal asymptote. Now, the letter E is the initial of the last name of Leonhard Euler, who introduced the notation because of f of x is equal to e to x, has special calculus properties that simplify many calculations. E is the natural base of the exponential function for calculus purposes. Okay, isn't it cool? It's like, hey, these things don't seem to be working out. I'm going to introduce this thing, and it's going to work everything. It's going to change the world. And that's how we came across this constant as you're looking at it. So it's kind of a neat thing to be able to have discovered. Now, this is the definition of base E. People go, well, Bloom, why are you doing this? I want to make sure, remember, E is a limit value. As we approach 1 plus 1 over x to the x power, okay, remember x keeps going in there, we keep plugging in values for x, it approaches 2.71828 as we make this comparison. Now, in our last graph, okay, there wasn't much of a change. It was more of a severe, it went up faster. When we looked at it at first, the first couple didn't seem to change much. But if we look and compare e to the 2x and e to the 0.7x, where e to the 0.7 power roughly approximates 2.014, okay, we're going to find out that the graphs would almost be identical. So if you take your graph right now, and instead of just, hey, e to the x power, make it e to the 0.7 x power, okay? In your graph, your y2, make it e to the 0.7x power. That's going to help approximate e to the 0.7 power is almost 2. It's 2.014, so that graph would be nearly identical. Okay, within 14 thousandths, excuse me. Now, we've seen this stuff before. Base E, have you worked with it before? Done logarithms with the natural log. Okay, done logarithms with the base 10. Now, an exponential function f of x is equal to a times b to the x. It can be written as, with b equal to e to the k, I'm just going to plug that in right there. B is e to the k becomes this. Okay, as we look that over. Now, if a is greater than 0, then it's a growth function. A is still greater than 0, and k is less than 0. But remember, I'm careful on that k less than 0. K's got between 0 and 1. Okay, it's between 0 and 1. It's decay. So make sure you get that picture. Make sure you look at decay and growth so you know the difference of the two. You know what's determining it. Okay, we've got 2 examples left. We'll probably get the one and then we'll save the other one for tomorrow depending on the time. We're out of here at 18 today. 13, I lied. I hate that. Hate that. Do we have time for this? We do have time for these 3. Okay, first thing. What's happening here? Is it a stretch or compression? It's 2. 2's inside. 2's inside. Horizontal shrink by a factor of a half. Remember, inside the function, it takes on the opposite of what you think. I know people, well, if there's 2 times exponent, but it's really half as big, okay? Because it's reciprocal of that value as we look that over. So that should look like that. Then it goes in, it shrinks it, okay? Here, negative x, that negative up there in the exponent should reflect across the y-axis, okay? So it should look like this. And then when it gets outside the function, I start working with my stretches and shrinks vertically. And so now I've got a vertical stretch by a factor of 3 for my last one. And remember, these graphs are there. They're a little tight. But this will be our last thing for today. By the way, the bonus problem is 5B, the extra example for your assignment today. Thanks, guys. Have a great day.